Today we're going to prepare a very unusual compound, manganese 3 acetate, which has manganese in the rare +3 oxidation state. We're starting here with manganese sulfate, and we've got 23 grams of the monohydrate salt, which is a faint pink color. We're going to start by dissolving this in 80 ml of water. Interestingly, the solution heats up quite a bit as it dissolves. It takes quite a bit of stirring to get it all into solution. Nearly there now. And now here's 16 grams of sodium carbonate. You can also use the hydrated salt, just adjust the weight accordingly. This is a slight molar excess compared to the manganese sulfate. We're going to dissolve this in 250 ml of water. And let's get a stir bar in there too. So we get this on the magnetic stirrer and get it stirring vigorously. The sodium carbonate has now dissolved. Now we're going to add the manganese sulfate solution. You can see a reaction generating manganese carbonate as a thick white, slightly salmon pink colored precipitate. Get this stirring vigorously for about 10 minutes to ensure we've got a complete reaction. On switching off the stirring, you can see the white precipitate slowly settling. Make sure you've got a good book to read, because we're going to have to filter this, and it's not going to be quick. Filtration took about 30 minutes. We washed the precipitate with about 50 ml of water. Then got the solid as dry as we could on the pump. This resulted in a pale salmon colored paste. We placed this into an oven at 120 degrees C for a few hours to dry it out. Here's the result. It's quite solid, but despite appearing dry, it weighs 25 grams, so it got at least 7 grams of water still in there. We decided to use the manganese carbonate as it is for the next step of the reaction. Here's our setup for the next step. We're using the 500 ml flask, and we've got an optional thermometer in here so we can check the temperature carefully. Here's 100 ml of glacial acetic acid. This is a large excess to what we need, but we'll be using acetic acid as the solvent for the next step of the reaction after this, so this isn't a problem. We place this into the flask. So now for the acid stirring vigorously, we're going to add a little of the manganese carbonate. It seems to go into suspension, and there's no sign of any reaction. So we add the rest of the solid manganese carbonate to the flask. And then we start to heat the mixture up whilst stirring. We use a reflux condenser so that we don't evaporate off the acetic acid. Interestingly, to begin with, it seems as though the mixture is becoming thicker in texture. By the time we're at around the boiling point of the acid, just over 100 degrees C, it's becoming difficult to stir. But the mixture slowly loses its viscosity and becomes stirrable again over the next hour or so. The color also starts to transform from a light tan brown to a darker color. We kept this stirring and heating at a gentle reflux for the next 4 hours. At this point the mixture was still opaque, but it looked as though the light brown precipitate had all gone. On allowing to cool, the mixture remained a liquid even down to room temperature. But any agitation and this quickly crystallized into a solid mass of light brown crystals suspended in the acetic acid, as you can see here. This must be manganese 2 acetate. Instead of trying to separate and purify this, we used this reaction mixture as is for the next step. So we got this back on the hot plate again, and on heating, the brown liquid rematerialized. We measured out the further 70 ml of glacial acetic acid and added this to the flask. Next we weighed out 5 grams of very finely powdered dry potassium permanganate crystals. We used a folded up piece of paper and a large bottle to crush the crystals. The paper is a work of art. Psychologists could work out all sorts of stuff from this. We've put the thermometer back into the flask as we want to track the temperature to see what happens in the reaction. We're starting at around 90 degrees C. Let's add a small amount of the finely powdered permanganate. The mixture turns a darker, more brown color, as you can see. Let's add a little more. After the second spatula we've got a slight temperature increase of about 8 degrees. So something is definitely happening. Here we are on complete addition. The mixture is a dark brown and the temperature is now 104 degrees C. We left this mixture stirring at this temperature for 15 minutes, and then slowly allowed it to cool down. There was no further change in the color or consistency of the mixture during this time. While the mixture was still quite warm, we poured it into a large beaker. Then we covered this with plastic wrap and placed it in the fridge to chill down. The first thing we notice is that on chilling there's no immediate crystallization as there was with the starting mixture. So something has definitely changed. Here's the mixture after left at about 10 degrees C for 24 hours. There's an chocolate brown, slightly orange colored precipitate in the mixture. The mixture is pretty thick and gloopy, as you can see. So we set out to filter this. The filtrate is still a very dark brown color, as you can see. The mixture took a few hours to filter, and tended to form a jelly of acetic acid and precipitate in the filter, which needed occasional breaking up and stirring. We got this as dry as we could, ending up with a large jelly-like lump of material. We know from the reaction before that this is going to contain a small amount of manganese dioxide. But it's not quite the right color to be pure MnO2, so there's something else here as well. We placed this in a makeshift desiccator containing calcium oxide. This should absorb both water and acetic acid. Over the next week the powder dried out and became a lighter chocolate brown color, as you can see. And here's the filtrate. It's still a very dark brown color. We added 5 ml of water to this, and then placed back in the fridge to chill again. After 1 week of chilling we noticed that some solid had formed in the liquid. We refiltered and dried this. This gave us a dark brown solid, still damp with acetic acid. On drying in the same way, this yielded the further 2 grams of similar quality product. Here's our original product after drying for a week over calcium oxide. It's a fine light brown cinnamon-colored powder. It still has a slight acetic acid aroma but weighs 40 grams. The theoretical yield with 100% conversion in every step is 31.5 grams of the anhydrous product and 36.4 grams of dihydrate. We know from the equations that the product should also contain about 3 grams of manganese dioxide as well. Let's do some tests to see how our product behaves. First of all, with cold water. Some of the product dissolves, forming a brown-colored solution, but it's not completely soluble. Now hot water. After a little while the color fades and a dark precipitate which floats on the surface is created. This suggests our product is able to hydrolyze in water, and is somewhat heat sensitive. Dilute cold potassium hydroxide solution. Once again we've got a fading of the color, and a dark brown precipitate formed, similar to the hot water test. Dilute cold sulfuric acid. Initially a brown-colored clear solution forms, but this then quickly becomes turbid and a dark brown precipitate starts to form. Dilute cold hydrochloric acid. We've got a yellow-brown solution, which, like the sulfuric acid test, slowly becomes turbid and specks of a dark precipitate form. A very dilute cold solution of iron 3 chloride. This is interesting. We have a dark brown solution formed with only a small amount of the product insoluble, and the solution seems to be stable over time. We're still making sense of these results and doing more tests on the product. But we've got something a little unusual here, and the description of the product perfectly fits the literature description for manganese 3 acetate. It seems to be easily hydrolyzed and unstable in aqueous acid and alkali solutions, so we'll keep it cool and dry. Stay tuned because this compound can apparently be used in some interesting radical reactions, which we hope to explore.